Hello and welcome. Further maths. Today we have a reduction formula. I did do the reduction formula in a different lecture, which was a little bit too advanced, but I thought I'll treat it today as a formula in its own right, not as part of a bigger lecture. So this is actually a little bit bizarre, first of all, because it does say to find the nth value of this particular integral. You're not likely to see something like that at your standard A-level further maths exam. They will ask you to do a recurrence formula. So something that looks, for example, I don't know, n is equal to some kind of function of n, maybe, I don't know, n over n plus 1, in minus 2. So that's the standard kind of thing that you're likely to see at A level. And then, of course, maybe they'll ask you to do a particular integral, maybe I4 or something like this. Okay, but for here, what this actually means is to find in not in a recurrence sense. So whatever you find, it could be, for example, in is equal to n to the 4 divided by, I don't know, by n factorial, something like that. So if you want to find I30, for example, you will put, of course, the answer is 30 to the 4 divided by 30 factorial. So you don't need to go back to the previous term and the previous term until you eventually evaluate it. So this is what we're going to be doing today. So let's start with the usual kind of approach to a problem like this, which is, of course, to write this as in, as per usual, integral 0 to 1. And how I'm going to write it now is the next thing. I'm noticing that this particular radical, if I write to the top to the minus a half, then it will integrate instantly if it has an x in front of it. So I will borrow the plus 1. That's perhaps why it's there. So I'm going to write it as x to the 2n, and the extra x I'm going to write it in front of the 1 minus x squared to the power of minus a half. So that's exactly the same. And from there is, of course, the usual integration by parts. Let's do it here. I'm going to differentiate the x to the power of 2n. So that's 2n x to the power of 2n minus 1. Let me just get out of the way. And I'm going to integrate this quantity. That's why I put the x there. So that is x bracket 1 minus x squared to the power of minus a half comes from 1 minus x squared to the power of positive half. The half times 2 cancels. It's just the minus that I need to take care of. So this is all I've got up there. So my next line now will become, this is equal to the product of those two quantities. So this is going to be a minus x to the power of 2n, 1 minus x squared to the power of positive half, evaluated between 0 and 1, minus the product of this diagonal. And on this diagonal we got another minus, so let's make it to a plus. And this 2n does not have x dependence, so I'm going to write it outside the integral. And inside the integral I'm going to have x to the power of 2n minus 1, and then I have 1 minus x squared. I do apologize, you can hear fireworks in the background. It's bonfire night, and I'm recording this, and I think some of my neighbors are having a party, although we are on lockdown, by the way. Okay, but I'm not gonna say anything. All right, so this is what we got so far. Let's evaluate this quantity. Is that good? Well, when x is equal to 1, this is 0, so that's good. And when we're putting x is equal to 0 now, this is 0. So in fact, this disappears completely. So what we're going to have is we're going to have in there is equal to 2n. And now the question is how we're going to manipulate this particular integrand. The way to go back to in's, we need to have things which look like this. So we need to have powers 1 minus x squared to the power of minus a half, which we don't have in there. In fact, probably I missed a step in here. I just wrote it straight away. But just in case we need to make reference to what is in later, let's write that this is in fact x. Not that it's difficult to see from there, but let's write it. And then we have, of course, 1 minus x squared to the power of minus a half dx. And let me rub off the workings for the integration by parts because we don't really need them. So, so we need to somehow change this integrand into something which looks like that. That's not the problem. The problem is now we have the wrong power here. It's gone to the power of a half. The way we're going to deal with something like this is probably to write it as follows. I'm going to put a square bracket here. So I'm going to write inside the square bracket x to the 2n minus 1 multiplied by the bracket that I'm after. The bracket that I'm after is to the power of minus a half. Okay, of course I changed the integral by doing so. And in order to balance it to be worth exactly what I had here, I need to multiply by 1 minus x squared to the power of 1. Multiplication of bases is the same as adding the power, so that's still worth exactly the same. I'm not going to bother to write the 1 in there. All right, after that, now what I'm going to do is clearly multiply this blue bracket times 1 and this blue bracket times the minus x squared, and let's see what happens. In is equal to 2n integral from 0 to 1. Multiplying that, of course, is times 1, it just gives me exactly the same thing back. 1 minus x squared to the power of minus a half, minus x squared times all of this. The x squared will raise the power of x now back to 2n plus 1. 1 minus x squared to the power of minus a half dx. So now I'm in business. I think I'm practically got my formula. So let's clear these two lines. I'm going to leave the initial line up there just for reference. And let's hope we've done it all correct. Unfortunately, I didn't write down the answer that I'm supposed to be getting. So when I get an answer at the end, I won't even know if I've done it correctly. I did, as I said, this particular reduction formula as part of the Riemann zeta 2 proof, which was a very long lecture. And I hope I remember the answer or something that vaguely resembles my answer. Just in case I get it wrong, and then of course I won't know. Okay, so we got this particular quantities. Now what is obvious, what we need doing in there is to split this particular integral into two. I hope you let me to actually do it there and just save myself a line. So if I put there another integral 0 to 1, but of course I got this 2n there, so let's make some room for it. So that's the same as that. As wrote as two separate integrals, and with it is their own dx's. Looks total and utter mess there. I do apologize. I just don't want to write this again. So we got that minus 2n, lots of that. Okay, quite clearly in is equal to minus 2n. This is exactly the same as my in, so that's definitely in. The question is, what is that? A claim, and is sometimes, unless you're familiar with recurrence relations that go in kind of like 2n plus 1, 2n plus 3, this is your in minus 1 with a 2n in front of it. The way to check it, just to make sure you're okay, because you might think, okay, I can't see this. Well, how can I check it? If you look what in is defined by having your x to the power of 2n. So this n is associated with this n here. So the question now is, what happens if I do n minus 1 in here? Well, the x in this particular integral, or this particular integral if you want, sorry, actually, right, I'm looking at the wrong thing probably. It's the same thing there, but it's best actually if we look at this. Otherwise it looks very confusing because the plus 1 makes no difference. So even if I was doing it the way I was just explaining it, they're still correct. But it's best to look at the original definition. Let's start again. In, little n there, is associated with x here being to the power of 2n plus 1. Look what happens now when I do in minus 1. The x needs, the power of x, we need to replace n for n minus 1. And if you look what that will simplify to, that will simplify to 2n minus 2 plus 1, which is 2n minus 1, which is what we've got in there. And therefore, this integral here is in fact in minus 1. So from this line now, we can get a recurrence relation for our reduction formula. And then we'll worry about how we're going to finish it off. So here's very easy. Move this in to the left. So we got 2n plus 1 lots of in is equal to 2n lots of in minus 1, which clearly says as a recurrence relation, we have this quantity here. So this is now, normally if you had this question at further maths at your exam, this is probably what you will be asked to show. It'll be almost certainly be a show rather than just get on with it. So how we finish? The answer is no. We need a closed form. So we need to manipulate this further. This is not normally asked in standard exams. I've never seen one of these. Well, at least in the last 20 or 25 years. I cannot really remember before that. So this is how we do something like this. I boxed it in the wrong place. The usage of my board is terrible. I hope my maths is better. 2n. So I'll write it again at the top because I'm running some space here. So I don't want to be in the middle of the board there. It's just very, very awkward. So this is now what we have got so far. And this is how we proceed. I'm going to get, without any values, I'm going to proceed one step by using this particular relation. So this is up to now, and now this, it gets fed back into that. What does that mean? Well, if it gets fed as n minus 1 there, it will produce something n minus 2 here. But the question is, what's in front of it? Well, that means the n minus 1 will be replacing the n's here and here. And that will give me 2n minus 2, if you simplify it. And if we put that in there, it will give us 2n minus 1. Okay, we'll do it again. So in is quite clearly these two bits there times 2n minus 2 over 2n minus 1. And we're going to take this now, we're going to place it there. So that's in minus 2. So we'll produce an in minus 3. And the n minus 2 of this will substitute in front of this one. So if we put n minus 2 in there and you simplify it, you get 2n minus 4, and on the denominator, even by looking at the pattern, I say, and in fact I write the wrong thing, 2n plus 1, 2n minus 1, 2n minus 3. Or if you want, one more from the top. Okay, so this is what will be happening. So we can generalize and say, okay, I can see what's going on. The top goes down in evens, 2n, 2n minus 2, 2n minus 4, and so on. While this starts from 2n plus 1, again, it goes down in 2s. So let's write these terms again and go to the very end where we would have finished, basically. So let's write this again. Loads of dots. And quite obvious at some stage, coming to the end, because these are always even numbers, it'll be 6. This is always bigger, so 6 sevenths. Then it would have been times 4 fifths times 2/3. I can't do more because, of course, the next one would have been 0, and I can't put 0 because with 0 there, the whole thing is gone. So the question is now what I will be at the very end. The way to see it is, if we look at this 2, and relate it to this quantity here, in order to get a 2 on the numerator, it means n here must be 1. So it's 1 there, and of course the 3 that we're seeing in there, that's the 2/3. But if we put n is equal to 1 in there, we have to put n is equal to 1 here, so that's your I0. So this definitely will be your in, if you knew, of course, what your I0 is, and perhaps you can simplify this mess. So let's start first of all by finding I0. So at least we got that out of the way. I'm going to do the I0 up here. I0 is that with n is equal to 0. So that's your integral from 0 to 1, x on the top over the square root 1 minus x squared. Very easy, because of course we've done it when we've done the integration by parts. You can write this as x bracket 1 minus x squared to the power of minus a half dx, 0 to 1, and this integrates instantly. Is 1 minus x squared to the power positive half with a minus at the front, and the limits are 0 to 1. I don't like minuses there, so I want to put a plus there and reverse the limits. So this will give me, when I put 0, it gives me 1, and when I put 1, it gives me 0. So your I0 is in fact 1. So I don't need to actually write this, so it's just times 1 there. So this expression here is my IN. This will always produce quite clearly some kind of rational expression. So we need to get a simplified form for something like this. I guess we can write it in capital Pi notation, but this is not going to be useful because it says find the nth value. So we want to know the nth value is that. So if I want to find a specific number, a specific value for your n, I have my answer straight away. So this is how we're going to approach this. The thing is, I've done that only the other day, as I said, as part of another question. I've forgotten how to do this one, and although I haven't done this for years, this particular question, I think I remembered it better the last time than now that I've done it only 2 or 3 days ago. So okay, let's look at this. IN, and I'm going to put a very long fraction, and on the top I've got 2n, 2n minus 2, 2n minus 4, times dot 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 6 times 4 times 2. On the bottom I've got kind of similar expressions going down in twos. This is all about manipulating expressions, and these are factorial expressions that you really need to have seen how to do some of this a few times and play around with them in order to know what it's doing. I'm not going to do anything just yet. I just want to raise your attention to the numerator. The numerator is actually quite nice because we can factorize a 2 out of each of those terms. And of course, if we factorize a 2, I'm not going to do it, but I'm going to show you. 2 times 2 times 2 times 2 all the way down. What you'll be left with, I'm going to put the power of 2 in a second. You're going to be left with n minus 1 from this one here, n minus 2, n minus 3, and so on. And when you get to the 6, it's going to be, of course, 3 times 2 times 1. And the question is, how many 2's did we factorize? Well, we can see from here. From 1 to n, we factorize 2 times 2 times 2, 2 to the power of n. And of course, all of this is 2 to the n times n factorial. So that's quite nice. The problem, of course, is the denominator. The denominator has odd numbers. That, of course, times 1 doesn't really bother us there, but it's not some kind of factorial as it is in there, 3 times 5 times 7, and so on, all the way up to the odd quantity 2n plus 1. It's not really a factorial as it is, but it can be written as factorials if you do a little bit of juggling. So I'm going to show you how to do this particular one. I'm going to rub off, perhaps, we don't need that, we can rub off the 3 lines above it and show you the tricks that you need to be able to do there. IN is equal to, very long fraction, I'm going to take this off. If we need it again in this form, I will write it again. And the top is not a problem, it's the denominator. I want to create a factorial on the denominator, so I need to insert quantities between these brackets in order to work. So I can start with 2n plus 1, leave a gap, 2n minus 1, leave a gap, 2n minus 3, leave a gap, dot, 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 and then we're going to have times, and we can put there 7 times gap times 5 times gap times 3 times whatever, very long fraction. And on the top we got a 2n. So I've just spaced it out. That's all I've done for the time being, and I hope you can follow what's going to happen next. Times dot, 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 and we got a 6 here, a 4 there, and above the 3 we got 2. Okay. In order to make a factorial on this denominator here, we need to have, of course, the missing term. And the missing term here is a 2n. But of course we can't just shove a 2n there. We need to balance it, and this is very easy to balance. Multiply top and bottom by 2n. So we have a 2n times another 2n. Now we go to the next bracket. Same thing here, 2n plus 1, 2n, 2n minus 1, 2n minus 2. And of course, we need to balance it. 2n minus 3, 2n minus 4, balance it again. Okay, so it would have been there 7 times, now we need a 6, another 6 there, times 5 times 4, another 4 here, times 3 times 2, another 2 there. I have no space to put a 1, but we don't really care about the 1s, even if the 1's not there, it's still a factorial. So let's look at what we have got so far and what is happening. Now the denominator is very nice. We don't have the 1, but it's no problem, yeah? You can't put a 1 if you want it, or 2 lots of 1 on the numerator. All of this is in fact now your 2n plus 1 factorial. Done. What is on the top now? On the top we've got 2n all squared, 2n minus 2 all squared, 2n minus 4 all squared, dot dot dot, times 6 squared, times 4 squared, times 2 squared. Can I manipulate it further? Yeah. What I can actually say is, since everything is squared, I can put a big square bracket like this and write 2n times 2n minus 2 times 2n minus 4 dot 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 642, and the squares that all of them have, pull it outside, just basic algebra like this. And of course at the bottom the 2n plus 1 factorial. Now, do you remember when I said to you in the beginning, I rubbed it off, but I'll do it again up here for just this line in there. I can factorize a 2 out of all of those terms. If I do that, I'll be left inside this quantity, and n minus 1, n minus 2, dot dot dot, 3, 2, 1. And of course I pulled out 2 times 2 times 2 times 2. How many? N of them. So this numerator, all of this, and don't forget the square, is this quantity here all squared. So let me just write it here. I'm gonna get to move out of the way. What's this cable? I'm gonna have In is equal to this quantity, which is all of this. And of course, what is that? That is of course an n factorial, and this is a 2 to the n in front of it. So on the numerator we're gonna have 2 to the n times n factorial, all of this, don't forget, all squared, and on the denominator is 2n plus 1 factorial. And this will simplify to 2 to the power of 2n times n factorial all squared, and on the bottom we have 2n plus 1 factorial. Okay, and I believe that is probably the simplest we can perhaps write the nth term the nth value of this integral. So this one is in fact equal to, maybe we can write this as 4, because 2 squared is 4. We can write it perhaps as 4 to the power of n times n factorial all squared divided by 2n plus 1 factorial. So for example, if they asked us in this particular question, you have this integral and they said to you, not necessarily to evaluate it using a calculator, but let's say perhaps, or they can ask you, or they, even if the calculator was allowed, they said to you, okay, use your calculator to find what is I-20 or something like that. Well, it's going to be a big number. I can actually do it because I don't have a calculator, but of course, your I-20, you don't need to find anything before that. It's simply 4 to the power of 20 times 20 factorial all squared divided by 40 divided by 41 factorial. So this one is going to be a fraction less than 1, definitely. The 41 factorial is huge compared to the 20 factorial all squared, and even that I think it will be under 1. So this will be the answer, and you could have actually worked it out. And I hope you find this useful. It's quite a tough question, this particular one. Do not worry, you will not get anything like that for your standard further maths, but you will get obviously the standard recurrence relations. But this is like a little bit of an extension to actually see how we can manipulate factorials, and you might find it useful for what's to come in your maths at a later stage. Hope you enjoyed it. I'll see you very soon. Who's laughing now?